Good evening, everybody. A very weird result here that's very, very believable, but it still needs to be proved nonetheless. Now, an integer polynomial means all the coefficients are a member of the set z. All right, I left that out right here. So all the a sub i's are a member of z. And the claim is that show a non-constant polynomial with integer coefficients, which is this representation here, cannot evaluate only to prime integers. Now, certainly we could trivially define a polynomial to be equal to 13 for all inputs, right? That is considered to be a single term polynomial, and trivially, it would be satisfied. So that's why we have the non-constant here. Now, if p of x is composite, that's the opposite of prime. A composite integer has a divisor less than the integer and greater than 1. So that's a composite. So if it's composite, we don't have anything to prove. So this is case 1. Now case 2, we can assert that if it's not composite, that means there has to be a value such that p of I evaluates to a prime for some integer I. Now notice this is equivalent to saying that p of I is congruent to 0 mod p, or p of I is a multiple of p. This is just congruential way of stating it, all right? Now also, we're going to look at this sort of obvious choice right here. We're going to take the same I we talked about and add multiples of p. M is an integer right here also. Let me write M, a member of the integers, right? And this is a natural attempt because look, when you expand this out, you're going to have multiples of p all over the place, and you don't expect this thing to possibly, evaluate to a prime number for all values, okay? Now, this part right here is true, this limit. That's just the behavior of a polynomial. It either goes to plus or minus infinity. I did the absolute value here just to avoid any problems. And you could put plus or minus infinity right here if you felt like. But that's just the behavior of a polynomial. It's a known behavior. It's called the M behavior, right? Now, this is since, though, we can say this because it's non-constant, right? Okay, that's what we're appealing to right here. Obviously it's constant, its limit's going to be the value of the constant. So we're appealing to this non-constant condition right here. But what does this really imply right here? This implies that P evaluated at I plus MP will be greater than P at some point, right? Will be strictly greater than P, all right? And we should put for some M right here, for some M. Okay, if this goes out far enough, you're going to reach a value greater than the prime, and that's crystal clear there for us. So we'll put some M, all right? Now that turns out to be important. It's not crystal clear why that's important. Now what is important, though, I guess, or no more or less important, is that the terms of P of I, P evaluated at I, which is posited to be a prime number, those terms, a sub n, I to the n, a sub n1, I to the n minus 1, those are a subset of this expansion. You get that from this very first term when you expand out each one of these guys. Now, just some commentary, and again, this is a pain to show super rigorously, but we know that I to the m plus p, I like this, okay, just let's say to k raised to some k power, right? Okay, we know without expanding this out that this is equal to I raised to the k, all right, which would be a term in this polynomial if we applied, a sub n, but that's not going to change whether it's a multiple of a p or not, but in any event, but this is going to be equal to I sub k first term, right? Plus some gigantic multiple, okay? I'll call it, what do you want me to call it? We'll say m sub 1 times m, right? M sub 1 times m. We're running out of names for constants here. I'll call it m sub 1 dot m. And right, folks, this hopefully we can get away with this, right? Because certainly I raised to the k power is the first term, and then you have mp multiplied against I, which is with whatever the binomial coefficients are, Pascal's triangle stuff. So you see, this is just going to be a big, huge multiple of m, and that's why this p of I being a subset of all these terms You see, and there's a lot of terms like this, but everything inside is going to be a multiple of m along with p of I, a multiple of p. Okay, what I said that wrong. M, that should be m sub 1 times some multiple of p. Sorry. Put multiple of p right here. My bad. Okay, some multiple of p, right? And so this truth, coupled with the fact that p sub I is equal to p, all right, means the following. And again, a little bit of a leap of faith here, but hopefully you believe me. That means that we can conclude by saying that p evaluated at I plus MP, okay, has to be congruent to 0 mod p. Now again, I could be super technical and expand it out and show you why it is, but hopefully this is very believable right here. Congruent to 0 mod p, right? But what does that mean? That means that p divides this, right? And so we get that p is a divisor and this object is greater than p, right? So that means this implies that p evaluated I plus MP is composite, right? If you have a prime divisor, that means you're bigger than the prime number right here. You see, this is crucial. If you're bigger than the prime number and you have p as a prime divisor, there's no choice but for this to be congruent to 0. Is composite. Let me just write it that way. That's I could say done right here if you want to, but we could say is composite. Okay, proving that the polynomial cannot take on all prime. That's what the claim is that we're trying to prove that the polynomial cannot evaluate to a prime number for all inputs, so it is composite. Okay, hopefully that made sense, folks. Hopefully it's rigorous enough for you. It really, I don't want to try to write it. You could try to expand it all out and show it a little more rigorously using the binomial expansion for an arbitrary k or whatever, or just substitute it directly in the polynomial and see it happening. But hopefully this is convincing enough for you guys. So we have proved what we set out to prove, that this polynomial cannot evaluate only to a prime output, okay? And the basic truths that we use, we made the assumption that p of I is equal to a prime number. We claim that p sub I, the terms in p sub I are a subset of p of I plus mp, right? And then a general term in the polynomial, notwithstanding the integer constant, is going to be I sub k plus some multiple of p. All of this adds up to the fact that this is congruent to 0 mod p, and it's also larger than p, meaning that p is a proper divisor of this object. P is a proper divisor of this object, this truth coupled with this truth. Therefore, p evaluated at I plus mp has to be composite. So shall we confidently or timidly call this a QED moment? Thus we've demonstrated. Okay, folks. Thank you all for viewing.